Okay, welcome Ramesh sir. How are you? Okay, in this lecture, I would like to introduce about basic Silvaco tool, how we can start to write any code or how we can understand the step by step everything. So let's start. I will share my screen first. Uh, I think my screen is visible to all of you. Please give me feedback like that.
Yes, sir.
Okay. So here we can see this is the PDF. In PDF, in this PDF, step by step with Atlas Silvaco ticket code has been listed. I will explain everything one by one. So first of all, this is started with the heading, getting started with Silvaco Atlas. What is this? Atlas is a physically based two and three-dimensional device simulator. What is the Atlas tool? It is basically used to simulate the 2D or 3D dimension devices. Okay. And it predicts the electrical behavior of the specified semiconductor structure and provides insight into the internal physical mechanism associated with device operation. Suppose you have a device like CMOS device. So this tool basically predict the electrical behavior and according to their structure, according to their doping value, and according to their physical mechanism. Okay. So these things we can understand by using this Silvaco TCAD. And before that, what we have to do, we have to write the code for getting any structure. Okay. So these things I will discuss in this lecture. So first is running Atlas inside deck build. So in the starting of the code, first term you will find Go Atlas. Okay. So what is the meaning of Go Atlas? This is the each Atlas run inside the deck build should start with this line. So this is the start line, Go Atlas. And during this lecture, I will also give you an example. So let's open my one example. I have uploaded one example, basic TFET. So here you can see the first line is Go Atlas sim flags equal to P this. This is the terms we have to write here in every program. So this is the starting term of the Atlas. Okay. Now next thing, what is this? Next one is second point is the order of Atlas command. So we have to we have to write some Atlas command in proper order. So first one is we have to define structure specification. Okay. So structure specification contains meshing, defined of the meshing, definition of the region, definition of the electrode, and definition of the doping. So four thing contains in structural specification. After that, we have defined models specification because without model, the electrical behavior in CMOS device is not possible. So what model we will use in our device, I will define that. It for different device, different model will be used. Okay. Now third point is numerical method selection. Means what? For getting your current value, your any electrical parameter value, you have to take a numerical method. What numerical method you will use, we have to define in our code. Okay. So we will see in my code. Let's now after that we have to find our result solution specification in the form of log file, solve, load, and save. Then result analysis will in the result analysis we can extract our value. We can see the plot using Tony plot. So this is the five terms we have to define in our code. I will discuss one by one here. Let's start using the command language to define the structure. So for mass value, first what we have to do, we have to define a structure. And a structure, first one is mass, then region, then electron, then doping. So mass value, you must find, first define a mass. The first statement must be mass space dot mul equal to that value. Means what happened? Let's see in our example here. Actually, in this example, I am using 2D structure, not 3D. So in 2D, we have two dimensional like X and Y only, not Z will define. So first I will define X direction, then I will define Y direction. And we have to do meshing of the structure. Why meshing is required? Because actually the performance of the whole device is not possible. So this tool will uh, calculate the performance of some particular region of the device. So we have to define that region, that is known as meshing. Okay. So in X direction we have to define Y direction as well. Meshing means we have to define our whole device in a small part. If this part will be as smaller as possible, then you will get better result. Okay, because if no part will be left, every part we can measure the current, and after that, that current will calculated after the algebraic sum. Okay, so meshing means just like a define the some specific and cutting the our whole device into small part. Okay, if I will give you one example, like you know, any structure or any material has a uh, unit part. Okay, you lattice structure, you know, there is a small lattice, a unit lattice, then you have to define whole structure. Like that we have to define or structure in a small part, that is known as meshing. So here it is written mesh space dot multi equal to 2. What is the meaning the 2? If 2 you have written, then what mesh value you have defined, it will automatically divide by 2. That by changing this value, you can change the whole meshing. If 2 you will write, so whole meshing will divide by 2. If 4 you will write, whole mesh will divide by 4. If you will add 0.5, whole mesh will divide by 0.5, automatic it become 2 times. So only changing this value, you can change the whole mesh value. Okay. So meshing is required to define the space of the device. It is important part. So suppose in my structure, if I will show you, just run this code, then you can see the structure. After then you will understand easily. So let me run this code, and let's go to the next point. So this is you must first define the mesh, and the first statement you have to write, the way of the writing mesh is mesh space dot multiplication value. Value may be 2.0, value may be 1.0, any value you can write accordingly, your mesh will change. This is the followed by series of X mesh and Y mesh for 2D structure. If you will use 3D structure, then X mesh, Y mesh, and Z mesh. Okay. For X mesh, you will write X dot mesh location. Okay. That value, spacing, then value. I will show you in my code as well. It's running. Okay, running. Here you can see X mesh, how it is written. X mesh equal to location minus 0.030, means minus 30 nanometer. You will write here in micrometer. Okay. In the SILVACO, everything you have to write in micrometer pattern. But you have to convert in nanometer. Like 0.03 micrometer means what? 30 nanometer. Understand? So minus 30 nanometer, from minus 30 nanometer is the leftmost point of the minus 30 nanometer, and you will go see the here till 80 nanometer. 80 minus 30, total length of the device is 110 nanometer. Understand? Started from minus 30 nanometer and reached 80 nanometer. So total device length is 110 nanometer. Okay. So my device length is 110 nanometer. So we have started the meshing from left point of the device. So our origin is started from. Let's check the structure. Then you will understand. Is running after the completion of this run. We can see the code and we can see also the result. Then it will be easy to understand. Face running that. Then I will show you how from where meshing started for X position, how meshing started for Y position, and what is the meaning of QTX dot mesh. Okay. After that, after meshing, we have to define region. After region, we have to define electrode, then doping, then contact. What contact you are using? After that, what material you are using? The material characteristics. Then models. What model you are using here? So actually we are using TFETs. For TFET band-to-band tunneling model we have used, non-local band-to-band tunneling model. And now this is the value, predefined value. After that, the voltage, drain voltage we have applied, then gate voltage, then we will see the output. Now I will discuss everything one by one detail, then you will understand easily. So let's run this code first, because with that structure you will understand easily. Anyone can understand easily. If structure is not in front of you, then it will be create problem to you. Wait for some time just. And here you can see this screen of deck build has been divided into two parts. The upper is used for the writing your code, and lower one is used as for the as a output. What value, what voltage you have applied, and at what voltage your device is running. Everything you can see here. Along with this, you can see the conduction, uh, conduction current value, transconductance value, everything. It is written. No need to calculate from here. Automatically, you will get at the output. Here you can see at drain what is the VA voltage, what is the junction current uh, density using the list. And my main point is what gate voltage your this code has been run is listed V gate equal to minus 2.25. So I have put the value from minus 1 volt to 1 volt. Okay. So negative part and positive part also I have taken. Now it reached at minus 0.3. We are reaching towards 0, then 0 to 1. Wait 5 minutes. I think after that we will get result. Now before it will execute, we will see here that our steps. So X meshing, what is the way of writing X meshing? X dot mesh space location. Location means suppose I started from minus 30 nanometer to minus 0.30. Not you have to write minus 30 because we have to write in micrometer. To minus 0.30 started, and what spacing you want. If space will be smaller, means you are doing very small meshing. And small meshing will take time to execute, but it will give accurate value. So we have to trade off between small meshing and time. Okay, we have to trade off between them. If you want fast execution, you have to increase this space. If you want late execution and good result, we can decrease it. Same thing Y meshing. So by using this way, you can mesh device X direction, Y direction. Here one example is also given. A simple mesh. Go at loss, mesh space. Here one given. One given means what? What mesh you have to define? it will divide by 1. Means what means you have defined same value it will consider. If you will write 2, the what means you have defined, it will be become half. Okay. So only changing this value, you can change whole mesh value. Otherwise, if this term will not given, you have to change all mesh simultaneously. I have mesh accordingly, according to your view. So this is the most good thing, and this is the way of doing mesh. Now, if you want to save your structure, how what is the format? Save space outf equal to your structure name. Here written simple. Simple means structure name is simple. Dot str, because you want to save structure file. So dot str. This is the way of writing saving. Save space outf equal to simple dot f. Simple, at the place of simple you can write your name, no issue. And that save structure you want to see on Tony plot. So at the same time you have to write Tony plot space simple dot str. If these two terms you will write in your code, automatic Tony plot will give you the structure in front of you. Here same here you can see is running minus 0.7. So after that, here save out f tunnel silicon source basics dot str, and that after same time I have written Tony plot. So when your this pointer will reach towards Tony plot, after execution of this line, you can see the structure. Okay. Now I think example is clear. Here you can see meshing. How small meshing is given. Dot dot dot. So simple structure by at loss. If this is the simple structure given and meshing has been defined like this. Same thing, no need to turn. Okay. Fourth point is specifying reason and material. After that, we have to define the reason. Means suppose if we are simulating CMOS device. CMOS device means CMOS less MOSFET device. So in MOSFET device, how many reason? Source region, channel region, drain region. Okay, this is the important region. Along with this, you can define SOI region below the your body, and after that you can define substrate region if you want. So along this is the because for particular region there is a particular value, particular region of X, particular region of Y given. So for defining region, you should know the X value, starting and ending X value, along with this starting and ending Y value. So region, how you can write region equal to number 1. This is the way. First region you are defining, that's why number 1 equal to material. What material you are using, that region you have to write here. Suppose silicon you are using, right? Material equal to silicon, and same time Y dot max is equal to 9.2. And here X value is not given. Uh, Along with this, you can define X value. If suppose top value, if I will show in my code as well, X minimum, Y minimum, and Y maximum. Along with this, X minimum and X maximum, you have to define. I will show you here. Reason number equal to 1. First reason I am defining X minimum minus 30 nanometer, X maximum till 0 nanometer. Means minus 30 to 0 is my source region. Okay. And this is the X region. Y region 0 to 10 nanometer. And what is the way? If you are coming here, like, let me show you. Suppose XY is given here. If you go upside, in Y upside, your Y become negative. Okay. And if you go towards right side, your X become positive, left side X will same. Means left side X is negative, right side Y X is positive, and upper side upside Y is negative, and downside Y is positive for this SILVACO ticket 2. So I am defining the reason. Okay. how much time it will take to execute. What is the gate voltage? Let me see. Okay, negative value is going to finish. Why it is taking time? Because the this meshing value is also very small. You can see 0.0001 micrometer means how much? 0.01 nanometer. This is 1 nanometer. This is 1 nanometer. So meshing is very small. And you can see our step size for gate voltage. I will tell you what is step size, what is final voltage, everything I will say. Step size is also very less, 0.05. So for moving from -1 to 1, it will jump from 0.05 steps. So this is very less. That's why it is taking time. If I will increase 0.5, so automatic your result will come soon. Step size is low. That's why it is taking time. And step size low means what? What you should keep? Step size low or high? You should keep step size low because you will get good result. Good point. Many points you will find. So then you can judge your result. If you take only 3 point or 4 point in your result, so how you can judge? This is not possible. That's why I have taken less step size. But what is the disadvantage taking less step size? Your speed of the operation execution will increase. So decrease, not increase. So you're taking time, no issue. So what we have understand meshing, X mesh and Y mesh. So please give your feedback. Did you understand meshing?
Yes, sir. Expression by miss.
Okay. Any confusion in this meshing? You can ask.
So, so the multiplication point is there, no, sir. Top MUL
Yeah. Multiplication point. Mesh
2 point.
space dot multiplies to 2.0. Okay. What is the confusion inside here?
So then with the it is divided by 2, sir. The spacing.
Yeah. Yeah. What is written here? It will be the divide by. Okay, not multiply. Here multiplied, may space multiply depend, but what happened? Suppose this is 1 nanometer, na?
Yes,
So
sir.
2 means what? Not 1.5 nanometer become it. Become 0.5 nanometer. If I will write 1 here, so what meshing you have to define? Same meshing become. Okay,
Mm,
this is the meaning of this.
okay, sir.
Okay, we can see here written like this. Multiplication point, I think they are not given. Given one is given, na? So one means what? Same thing, eh? No need to multiply. If you divide any value with one, you will get same value. Okay.
Yes, sir.
So you can put one if you have confusion, no issue. Okay. You can put one
Okay.
and you have defined what you will define, same value it will take it. So that's it. And
Okay.
here, mesh, after the meshing, you can see it is given qtx dot mesh. qtx. Actually, this code is for uh, tunnel fit. You have heard about tunnel fit before? Yes, you have. You are working on that, na?
Ah, yes, sir.
Okay. So, tunneling happen between at the junction of source and channel. You know,
Ah, yes, sir.
tunneling happen at the source of junction and at the junction of source and channel. Okay. So, we have to define the some reason where tunneling may be possible to be occur. So that's why here QTX dot mesh is given. QTX means quantum tunneling of X. Okay. Quantum tunneling of X means if you will define region at the source, so you have two X value, minimum and maximum, and two Y value. Okay. Not getting. Here. Suppose here I am defining tunneling. Suppose here. Okay.
Okay, sir.
So we have to define some region for tunneling. Na? So suppose one X here, one X, two X here. Okay, this side. So that's why it is written like here QTX. Dot means equal to location minus 20. Actually, my device is starting minus 30, but I thought that minus 20 point and result plus 20 point. Here the
Hmm.
reason for tunneling may be possible. Okay, you can take minus 10 plus 10, no issue, because tunneling region is very narrow.
Hmm.
Okay. But here for the safety, it is taken minus 20, 20 plus 20 for x. Okay, and
Okay.
why what why x is 2x more is given? Because tunneling not only possible at source and channel junction, it is possible also at drain and channel junction. You know, but we want less tunneling towards drain and channel junction. But still we have to define it. Okay, that's why 2x is given. You can see. So minus plus 30 to 70. This is the region for drain side. Okay.
Hmm.
So but for both x region, y will be same. Y will be same na 0 to 10 nanometer.
Um,
That's why only one y region is given and two x region is given. For source tunneling region is most important as compared to the drain tunneling. You can skip that one, drain one, no issue. But I have included everything in my code, every possibility. Okay,
okay, sir.
okay. Because we want less tunneling towards drain, we were more tunneling towards source. Uh, if tunneling will occur at drain, what happen? You know, the leakage current will increase. Leakage current will increase when tunneling will occur towards drain side. So we have to minimize tunneling from towards drain side, from channel to drain or drain run. Okay, but still we have to define. That's why I have taken this value. Just try to understand meaning of this code. First time you are listening, na. So try to understand everything. After that, you will write. You will do practice. Automatic, you will understand. Okay.
Okay, sir.
Yes. So I think you have understand the meaning of meshing and quantum tunneling. Now reason I have also told you about that. Still, I want to show you my structure. That's why I'm waiting for that. How much left? Okay, it's then now negative part has been completed. Now positive part is going on. 0.05. Now it becomes 0.1 till 1 volt. After that, we will get result. So 19 step size remaining, not 10, 19. So, because I have taken less step size, no, that's why it is taking time. In the next time, I will take a higher step size. Automatic, it will run within 2 minutes. So this is the how your deck will work. First, you have to understand how to write code. Suppose I will give one when you will understand this code, na, what I will do, I will give you one code. Suppose you want to work on vertical TFET. Okay, so first draw your vertical TFET on paper. Okay, define all value x, y, everything, and after seeing that structure on paper, you can write this code easily. Maybe one first time, second time, third time, you will get difficulties. But when you will understand everything, na, it will very easy. It will become very easy. So my motto is you have to learn. Okay, anyone, you have to learn how to write. If I will give you direct code, suppose you will run and you will get some value. Okay, if you get some value, but you will not understand how you are getting value, what change had been changing has been done here, and what if I will change something, you will not understand. So it will be not good, good research. So
Yes.
first I will teach you. I will teach you along with other person because this video is downloading and not downloading. Uh, what is recording? I will try to upload this in my YouTube channel. And who will see? You will try to learn. If he will understand, or he or she, anyone will understand, then easily, I think, who will see this whole lecture, he will be clear what is the meaning of all part of coding and how you have to write. So keep patience. Just three part we have completed: machine, quantum tunneling, and reason. I will teach you again. I'm waiting for my structure. After that, how electrode you can define. Electrode means what? Suppose you have MOSFET. In MOSFET, how many electrode basically? Source, drain, and gate voltage. You know. So electrode means what? Where you will apply the battery. At the point where has been kept here same. Okay. So the same, only three electrode we have: drain electrode, source electrode, gate electrode. Number one, number two, number three, according to your which one you want to number one, number two. And your electrode length from X region, electrode length Y region, this minimum and maximum. You can write, you can write. Because everything you have to define in region. How this tool will understand at particular region what kind of electrode has been defined. It's not a human being. It will see the your reason, and that reason it will understand. Okay, drain reason, drain electrode reason. Until here, it will understand source electrode reason. So we have to define regions like that for electrode, along with the uh, particular region for doping or material definition. You are defining material here, na? So that's why I have written. So this is the way how you can write electrode. After that, now you have already defined region and electrode. Now you have to do doping in particular region. If you want higher tunneling current, for that you have to do high doping in source region as compared to the channel and drain region. So how you can do? Right here, doping. What kind of doping you want? Uniform doping, Gaussian doping, lots of the way of writing doping. So basically, we are doing uniform doping. Uniform doping means the doping value at this particular region everywhere will be same. Gaussian doping means at the middle one is the highest doping. If you move towards left or right, doping will decrease. Okay, so what kind of doping you want, you can write here. So doping equal to uniform. I want uniform doping. Now space. What concentration you want doping? Right here. What kinds of doping? P-type doping. And direction. Direction Y. Direction Y means what? Actually, uh, in the fabrication, doping started top position, means not a vertical. Means if you are doing doping from top to bottom, means upper side your dopant will be there, and doping will your dopant will fall on your device, and doping will start. That's why direction Y. Okay, because lateral doping not possible. And this is the for region one. Region means we have already defined. It will the consider region one for this doping. Now here, if you write region two, so for region two, it will define this doping. So according to writing this 1, 2, 3, it will automatically catch that point, and that value will doping with that this value. So three region we have defined in this structure. Uh, Region one is source region, region two is channel region, and region three is drain region. Now our uh, simulation has been completed. Now we will see the result first. In result, we will get two value. One is structure, and second one is your current value, or what value, electrical parameter you can see. This is crack Silvaco tool. Now that's why it is taking time. And if you will on genuine Silvaco tool, it will run very fast. So here you can see Tony plot has we are is here generated here, and two thing you can see here. Left side one is a current. In current means gate ID VGS. VGS means gate voltage. ID current versus gate voltage. And here right side you can see the structure. What structure I have defined in my code. Now you can see our first here come here at bottom side. Zero here. This is the junction source and channel junction. I have taken zero for X, and at right left side of the zero is negative and right side of the zero is positive. So till left side till minus 30 nanometer, and left right side till 80 nanometer, as I have defined in the meshing as well. Minus 30 nanometer is starting and 80 nanometer. So meshing will start minus 30 to 80. And you can see somewhere written 0430 and somewhere written 20 only. Why it is? At the junction, suppose where is the junction? At junction, this junction, source junction, drain junction, I have done very small doping, very small meshing. Is a dense meshing you can say. Dense meshing why? Because if meshing you will do dense, your result will be good. If you do very what you can say rare meshing, you will find not a good result. Dense meshing will provide you good result. That's why at the junction I did dense meshing, you can see. So at 0 point left and right side I did dense meshing. At the beginning point also I did dense meshing. Where you had drain and channel I did dense meshing, and last point is missing. This is the reason why I did add like this. Okay. Same we will do Y. So go to Y direction first. Y started here 0 to 70 nanometer. So you can see if you are going towards downside in Y direction, your Y become positive. If you go upside of the Y, your Y become negative. Okay. So you can see this oxide is in the negative part. If oxide thickness 2 nanometer, so minus 2 to 0 thickness will be of oxide. If 1 nanometer, minus 1 to us, we can see what value I have taken. Minus 2. That's why it is written minus 2 nanometer, because I started meshing up by from oxide, and oxide is lying in the negative part. So, and what is the thickness of oxide? 2 nanometers. So that's why it is written minus 2 nanometer till 70 nanometer. Understand? Same. Quantum tunneling I have also discussed here. This is the junction. This is the junction for source and channel. Minus 20 to 20 is the tunneling region, and Y direction 0 to 10 nanometer. Same here. Suppose what is the value of that? What is the value I have to consider? Minus 30 to 70 nanometer. So minus 30 will be right here and 70 here. So for that also y is same. So I have written y one times only, not write same value again and again. And now this is your source, channel, and drain. Now below this region, I have taken a SOI, means a oxide region, 10 nanometer to 16 nanometer. It means total 50 nanometer thickness of the oxide I have considered. This oxide is silicon dioxide, SiO2. SOI TFET. That's why it is called SOI TFET. And after that, I have defined a substrate, silicon substrate, 60 to 10 nanometer of thickness, 60 to 70 nanometer. So this is our structure, what I have defined in this structure. You can, if you go to region 1 is source region, because this is minus 30 to 0 and y 0 to 10 nanometer. And in this region, what I have considered silicon. Now region 2, 0 to 50, this is the channel region, also silicon. Region 3 is drain region, also silicon. And region 4, minus 30 to 0 and minus 2 to 0 is Si3 and 4. Si3 and 4, why I have considered this is just like a air. because the dielectric constant of Si3 and 4 is equal to 1, and the dielectric constant of air is also 1. So at the place of Si3 4, you can directly write air, no issue. Your result will be same. If you write directly air, your result will not change. So air is not looking good. That's why I have written Si3 N4. That's it. See, this is the material which dielectric constant is same as the air. Why we need to define this region? Air means what? This region here. Before this oxide and this region and this region. After this oxide, upper part of the source and upper part of the drain. You can see Silvaco only consider a rectangular structure. If air you will not define this, this will be not a rectangular, because here zigzag will be occur like gap, then oxide, then gap. This is not rectangular. So for making this rectangular, we have to define any value. Okay. So because actually this is the air, so we have to define air as well. At the place of air, you can write Si3 and for no issue. Directly you can write air. You have to define, you have to make it rectangular anyhow. You have to not make it cut point like a this lower part, then upper like that. You could not define here in this Silvaco. This is the, you can see disadvantage of Silvaco if you want. So that's why I defined Si3 and 4 here. Si3 and 4 means what the value? Minus 30 to 20, minus 2 to 0 value. Okay. Same SiO2, S4, other our oxide value we have defined, then and same Si3 and 4, then 50 nanometer SiO2, then silicon substrate. This region I have to define till 8 region I have to define. Then electrode I have also told you. Electrode means what? Source electrode. Source electrode means if you can put electrode this side, you can put here. If you can put electrode upper side, you can put here minus 32, 0. Electrode thickness is, 0. Length is what? 0 to, sorry, minus 30 to 0. But thickness will be very small. Means no thickness required. So that's why here, here 0, if two way, by two way you can define it. If you want to connect electrode at y direction, and other way you can connect electrode at z direction, no problem, no any kind of change in output will occur. So in my case, what I have considered, drain, first for drain, it is considered this y direction, 82. What is the value of y? Here upper side and lower side, both direction, both has x has same value, you know. So 80, x 80, x 80. So that's why it is written x minimum 80, x maximum 80. Your x is not changing, na, but y is changing. Y is 0 to 10 nanometer. Right? 0 here, 10 nanometer. So this electrode had been defined for drain. For source, what is the x value? 0 to 0. Your x is not changing because y is changing 0 to 10. So for source, you come 0, sorry, not 0, minus 30 point, na. It is minus 30. This terminal point is minus 30, this point is 80. So minus 30, minus 30, and y are changing 0 to 10. Same gate, if I will see the gate is started from 0 to 50. X value 0 to 50, and thickness is, I'm not considering thickness of the electrode. Na. If you will consider thickness, then you have to define the material also. What kind of material you like, aluminum, polysilicon, copper, what material you are using, then you have to define. If you don't want to define the material, don't define thickness. Only x value you will define here. If y value you will define, the thickness will occur. So that's why here you can see 0 to 50 nanometer, and thickness is same, minus 20, minus 2 nanometer, minus 2 nanometer. I'm not defining. So no need to define material as well. It will automatically consider what work function you are using here. I am using 4.7. 4.7 means aluminum, almost aluminum. So, okay. So automatically it will consider aluminum. So two way you can define the thickness if you want. If you have to, you will define, then you have to define that material here also. So no need to define. Only change the work function, automatic it will take. So this is the way how you can write electrode. Now doping, I have also taught you how you can write this. This is the comment box. If you don't want to run any command, just write has in front of this command. Automatic it become comment. Means your during the simulation, this tool will not run this line. It will consider as a comment if you put has here. Okay, so here something is given and Pharaoh and like that in my code, but in this structure I don't want to run it. That's why I put it as a comment. If I want use this, then I will remove this has, automatic it will be part of your code. So in this lecture I am doing basic thing. So just learn basic thing. In my next video or other video I will teach everything very in detail. Now contact. Contact means what? Three type contact I have defined is drain, source, and gate. So I don't want. I'm not interested for what kind of material using drain, what kind of material you same. But our gate material is important because the gate voltage is the main factor for controlling the device. You know, that's why it is called voltage control device. Na? So the gate voltage is more important than the drain and source voltage. Drain source voltage just used to pull the electrons. Okay. So that's why gate work function I have defined, and other I have did neutral. It will, this tool will consider according their neutral value. Okay, so gate work function 4.07, you can define 4.0, 5.0, whatever material you are using. Go and Google that material work function. You will find that work function right here. Automatically, this tool will consider that material. So what gate material you are want to use. So gate work. This is the way how you can define your contact value. Now, in my whole device, I am using silicon semiconductor only. Okay, I am not using other semiconductor like germanium, gallium arsenide, or gallium antimonide, or indium phosphide, or whatever. I am not using that material. So I am not no need to define that material. I am using silicon. So only define silicon. You have to define that material. How this tool will understand what material you are using? Only because only through this code. It is not a human being. Okay, so it will understand through this code. So you have to write everything in your code. So material, this is the way how you can define material. Material space material equal to what material? Silicon. And you have to write the effective mass of tunneling, effective mass of your silicon. It is the 0.2 h into the your rest mass. Now rest mass, this is the ratio of effective mass and rest mass. It is value 2.0 for silicon, and this for holes it is 0.24. You can Google it. You can find easily on Google. So right here that value, the ratio of the effective and rest mass. Okay. And along with this, you can also define other values like band gap and other values. What? Mm, okay, so let's left it. No need to define because silicon is a common material. So just you will write silicon and this value, automatic the tool will consider the silicon. Still, if you will not define silicon, it will consider silicon because silicon is common for every tool. But if you are using new material, na, you have to define everything. Otherwise, you will not get proper result. So this is the main point you have to understand. If you are using new material, you have to define everything. Now, this is about material. Now, what is models? Okay, models is most important part because model without model, your device will not run according to the proper way. Like if you want tunneling, band to band tunneling, because TFET use band to band tunneling from source to channel. So for that model is defined already. So what how you will write models BBT dot non-local BBT dot uh, and L drives quantum dot direction equal to 1. This is the way you have to write. No need to write run, just copy paste. I will tell you. Now upper model is CVT, current voltage SRS model, band gap narrowing, Fermi. It is right like that because band gap narrowing we are using for tunneling. That's why these two model basically used for TFET always. Just copy paste. Now here direction equal to maybe 0, maybe 1. So what in the what case it become 0, in what case it become 1? You can see if direction equal to 1 means your device is lateral. If direction is 1 means your device is lateral, means our current is flowing from X direction. If direction is 0 means your device is vertical, your current is flowing from Y direction. So in your case, if you want work on vertical defect, you have to write 0 here. Okay? Or everything will be same, no issue. Now this Newton Raphson, actually, some what kind of mathematical terms they are using in this tool. Actually, Newton Raphson method you have also learned in your mathematics. So Newton Raphson method is the algebraic calculation. Okay, so this is the good method. So in this tool, Newton Raphson method they are using the Newton carrier value. This value is already given. You have to not change. Just copy and paste. Okay, this is the value given. Time, how much time it is taking. What is the trap value? What is the maximum trap value? If you will change any value, automatically result change. No need to change this value. This is the material property. No need to change. You have to copy paste like that. So here you can change. Means in your CMOS device like MOSFET or TFET, you have two main voltage. Which one? Drain voltage and gate voltage. Source voltage are mostly your source voltage is connected with body voltage. Okay, for why it is connected your source voltage is body voltage? For reduction of the body effect. So no need to define your source voltage here because source voltage is common. Common means connected. So only to define drain voltage and gate voltage. So here you can see, first I will define drain voltage. This is the way of writing, how to write. Solve in it. Okay, solve in it. Solve V drain starting point. Give some value like very small value 0.001, 0.001. Very small value you have to put. Now we have to define a reason of the source drain voltage, minimum value and maximum value, and what is the step size. Step size means suppose 0 to 1 voltage. So first it will apply 0 voltage, then apply 0.1 voltage, then apply 0.2, then 0.3. It will increase like that till 1 voltage. So this is the way of writing of the drain voltage. It when all voltage will complete it, automatically drain voltage has been applied 1 voltage, then you will increase the gate voltage, and according to this your current will change. So first we have to apply drain voltage like this. You can change 1 voltage, 2 voltage, 3 voltage according to your wish. No problem. No one going to ask a question. Okay, if you increase the drain voltage, your current will increase, as you know. Okay, and the step size, if you reduce the step size, your the speed of operation of this device will reduce, and if you increase the step voltage very fast. Okay, now your current, you want to see the current here, this current. This is the log file. You can see right here, data from tunnel silicon source basic dot log. Okay, log file. So current or any value, any plot will always show you in log file, and structure file you will show always in str file. So str file I have already defined, but log file also we have to define because we want to current. So what is the way of to writing this? Log space out here equal to your device name. You can write anything here. Dot log. You have to write after the drain voltage. Then you have to apply gate voltage. In my case, I have used minus value also of gate voltage. That's why I have written here. If you want only positive to negative value, just write 0 to 1 voltage, step size whatever you want, just like drain voltage. Okay, in one way. But I'm using also negative value. That's why it is written. Along with this, the gate is written, name is equal to gate voltage, and If you want apply a small gate voltage, means pulsating voltage. Pulsating means AC voltage also is the also of the your part. When you will apply AC voltage as gate, that means you want to see the RF property, radio frequency property of your device. If you will not include AC volt frequency, that means you want to only see the DC result. But if you want to see the AC result, then you have to apply a frequency also. 1 megahertz generally everyone use at the basically. So I have written here AC frequency 1 megahertz because I want to see the AC property of my device. So here is the way how you can apply drain voltage, how you can apply gate voltage. It is the way right like this. Now what result you want to see at output? What how you will write output E field recombination. We want to see the recombination property. We want to see the band parameter like conduction band, valence band. So we have to just write here, just copy paste, no need to change this. I've been trying to tell you what is this. Mobility, x velocity, means x direction velocity, y direction velocity, electron velocity, impact, flow line charge, drift current, diffusion current. This is the result you want to see in your device. That's why it is written in output. Okay, so just copy and paste in your code, no need. Only what you have to do, you have just do machine. Okay, you have to define just reason, electrode, and what amount of doping you want. And this thing, I think same thing, this will just copy paste. Okay, if you want change voltage, otherwise will be same. So everything you have to return, and we want to save our result in str file. What I have also taught you in starting. Save AutoF your device name str. We want to see in on Tonyplot channel silicon source basic.log and .log file and str file we want. Just copy paste this is log and str. Okay, this is the way. And now we want to extract some parameter like threshold voltage. So this is the formula for threshold voltage extraction. No need to just you will see result here. Okay, where is this? Okay, so if you want extract threshold voltage, write here. If you want extract sub threshold swing voltage, you can write here. This is the way of extracting your data from your result. Here you can see come below this code here. This I want to extract my threshold voltage value comes 0.361 volt. You no need to calculate. You will directly get your threshold voltage. Our sub threshold swing comes 0.0245 volt per decade, means 24.52 millivolt per decade. Okay, this is our threshold sub threshold swing. So this is the most important parameter for TFET. And how you will get this parameter? By using this formula step by just copy paste, no need to do anything. If you want, if you will change your electrode name, then you have to put that electrode name here. Okay, if you're not going to change, so no issue. So this is the code. What is the meaning of all lines? What is the meaning of all part? I have taught you very clearly. I don't think you have doubt. If you still have doubt, you can ask your question. I'm always ready to answer you. And I will share this code to you. Try to implement by your side. And what is if you want work on vertical TFET, first draw on vertical TFET from any published paper. Then try to write code first according to this. Okay, because my structure is this, and the code for this is given here. Okay, no issue. You can see. Now you have to draw your structure on your pen copy and try to write code. Then you will understand everything easily. So I'm not saying that you will able to write code at first attempt. Just you have to try. Okay, so this is the all about this lecture. So let's 1 second. So I will stop recording first. then I will talk to you.